Hello, everyone. Welcome to today's live broadcast, Vero Cell Cultivation for Vaccine Production. I'm Feliza Mirasol, the Science Editor of BioPharm International, and I'll be your moderator for today's event. We are pleased to bring you this webcast presented by BioPharm International and sponsored by Eppendorf. I would like to share a statement from our sponsor. Eppendorf is a leading life science company that develops and sells instruments, consumables, and services for liquid, sample, and cell handling in laboratories worldwide. By exploiting the strong synergies in bioreactor technology and polymer manufacturing, Eppendorf has emerged as a global player and valuable resource to its customers in the bioprocess marketplace. Eppendorf was founded in Hamburg, Germany in 1945 and has more than 3,000 employees worldwide. The company has subsidiaries in 25 countries and is represented in all other markets by distributors. We have a few important announcements before we begin. This webcast is designed to be interactive, and we encourage you to ask questions during the event. You can submit questions by typing them in the Q&A box, which can be found on the right-hand side of your screen. You can enlarge the slide window by clicking on the small square icon in the upper right-hand corner of the slide window, or by hovering your mouse over the lower right-hand corner and dragging the window to the desired size. The slides will advance automatically during the event. If you have any technical problems viewing or hearing this presentation, please click on the question mark help widget that is located in the dock at the bottom of your presentation window. I would now like to introduce today's speaker. We are pleased to be joined today by Michelet Dorsays. Michelet Dorsays has been a bioprocess field application specialist at Eppendorf, North America for more than 6 years. He supports customers with his expertise in cell culture and microbiology bioprocessing by providing application support and system optimization, and by conducting demonstrations, testing, and evaluations of technologies. Before joining Eppendorf, Michelet has worked for global players in the pharmaceutical industry, from performing hands-on experiments to managing all aspects of reviewing bioreactor scope and system design. He holds a bachelor's degree in biology from the Salem State University. Thank you for joining us today, Michelet. Please go ahead and get us started.
Thank you for the introduction. Thanks everyone for being here today. I appreciate you being here. So today I'm going to discuss with you briefly the application note that was generated in our in-field application lab by Amanda Saddle. And today I'm going to discuss with you the application note we did on cultivating Vero cells for vaccine development. The agenda, we're going to cover a brief introduction on vaccine, looking at some of the technology that's available for cell retention device for adherent cell line. And we're going to look at the cultivation of the Vero cells in the bioreactor. And we're going to continue with the importance of high quality pre-culture in a bioreactor, and also the power of process monitoring control, and hands-on expertise for cultivation of Anchorage-dependent cell. Also, throughout this presentation, you're going to see several of QR code, and this QR code have in them information that if you would like to see more information, you can pull out your smartphone and scan the QR code, which will provide you with more information. So, for example, this particular QR code will connect you to the Eppendorf website, where we have a lot of bio expertise information that you can use to be as a guide and use as a starting tool to help guide you to different processes that you are working on in your lab. All right. So vaccine, just a brief background on vaccine. So there is 5 major types of vaccine. The number one, the most commonly used vaccine is what we call the live attenuated vaccine. And that is a modified, sort of like a weakened, but still a living virus or a bacteria. You get injected to the body to generate a immune response. The second type is called the inactivated vaccines, and this vaccine uses the kill version of the disease-causing germ to stimulate a immune response in the body when administered. The third vaccine type is the toxoid vaccines, which is a immunity against the disease-causing product of the germs. You have the subunit, recombinant, and conjugated vaccines, which is the immunity against a specific piece of the germ. And fifth type is the nucleotide vaccine, which use DNA and RNA that code for an antigen from the pathogen. So, reason why we decided to do a brief kind of like application note on vaccine production, given the current pandemic and what's going on right now, where we have researchers across the world in a rush to come up with a vaccine to help combat this current pandemic. So we thought it would be a good starting point to help generate some content and to help contribute to the fight against COVID. Challenging vaccine. This slide is going to go over some of the challenges the vaccine industry face to commercially and viably produce vaccine. So the first thing they're looking at is cost saving. So when you manufacture a vaccine, it's important to take into consideration the cost, because you don't want to produce a vaccine that is too costly for the end user to be able to afford. So therefore, its cost is definitely a very important factor, because you want to make sure that it is accessible and viable for everyone that's needed. Second, it's safety of the product as well as the operator who's manufacturing the product. So you want to make sure that the product that you are manufacturing is not causing any harm to the person who's going to take it, and also for the operators who's manufacturing those drugs or those vaccines per se. Okay. Second, the third aspect, I should say, is the flexibility. So the vaccine has to be flexible. For example, if you produce the vaccine, that you should be able to administer it no matter where you are, whether you're in the field and where there is not a lot of resources available, or you're in a hospital setting where there's a lot of resources available. So the vaccine has to be able to transport accordingly based on certain different control environment per se, based on temperature and the ability to access it, whether you're in a remote area or in a closed facility. The fourth aspect is time efficiency. Time efficiency is probably a very critical as well. You want to make sure that you are able to develop a vaccine in a timely fashion, in a timely manner, to make sure that it is readily and easily available so that you can help combat the current pandemic that you're facing. And also faster time to market. You want to make sure that you bring the product to market as quickly as you possibly can to make sure that you cover all the safety aspect of it as well. In this slide here, we're looking at the bioprocess development process. So the first aspect is the cell line development. So after you have established a particular molecule of interest for the vaccine, then you establish a cell line that you're going to use throughout the manufacturer and also doing some development work as well. Second aspect is media development. So you have to find the proper media that the cell line you just developed will be able to grow and be happy with, sort of, I want to say it that way. Then next, you will move into what we call an upstream bioprocess. So upstream bioprocess is taking the cell from the small-scale bioreactor and do your process development, transition to bench scale, and move on to pilot scale and into a production scale. we call that a scale-up. So upstream process, bioprocess development, referring to the small scale all the way up to the manufacturing scale, and sometimes include harvest clarification as well, depending on the company. The next step you have is downstream, which then take the process after harvest clarification and all the way to fill and finish, which sometimes including the vial, which get administered into the patient itself. Here, we're looking at some of the upstream bioprocessing technology that's available to help the scientists, bioengineering, and the lab accomplish their tasks. So here at Eppendorf, we have numerous solutions that help in the industry to help combat the current pandemic. So for start, we have what we call a parallel system, which is a parallel processing. So we have system that allow you to do simultaneous tasks at once and using up to 24 different vessels. We also provide single-use technology. Our single-use technology, our rigid wall vessel, really is mimicking the glass vessel, so that making scale up from the single-use technology to the large scale effortlessly, because they follow the same geometrical shape. And you have, of course, the system you have in-house got to be scalable. So for example, if you're developing a process at the small scale and to transition to bench scale and pilot scale and to production scale, you want to make sure that you're using system that you are able to easily to scale up the system. At Eppendorf, we have that covered. We've been in the industry since the 1960s with combined experience with the old New Brunswick legacy and the acquired of Dascape products. So we've been around for quite some time, covering both the hardware as well as the software as well. And the efficiency use of data. So that's probably the most important aspect of it all when doing bioprocessing in the upstream, because you want the data to kind of like dictate you to the next step that you need to take in order to achieve the desired end goal or end result. So now we're going to move into the cell retention technology for attachment cell. So most commonly application used in vaccine productions is what we call perfusion. And here on the slide, as you can see to the left, we have this graphic kind of like showing you what perfusion is. So perfusion is when you're taking in fresh medium, you constantly add it to the bioreactor. And as you see, at the same time, you are also removing source of media, but you have what we call a cell retention device in the bioreactor, which kind of indicate in the white circle in the bioreactor image here as illustrated, and the cell remain in the bioreactor. So some of the benefit that provide when you're doing a perfusion application run is that you get to remove some of the toxic byproduct out of the bioreactor, provide the cell with a more healthier environment so they can continue to grow. You also replenish some of the nutrient that's been depleted by the cell. You also have a more constant process condition, meaning that you don't have increase in like the byproduct toxic waste, so you maintain a constant environment that the cells like to grow. And it will also help you achieve a high cell density, because that you have the capability to retain the cells in the bioreactor as you provide them fresh nutrient and they continue to replicate. So you have the number of cells increase in the bioreactor, which in turn will increase the product of interest, and which in turn will increase the product of interest and provide you with a shorter duration time for the product and the culture. In this slide here, we're looking at some of the fill retention device technology for adherent cells, excuse me. So for example, here to the right, you're seeing what we call the spin filter with a pitch blade impeller. And this technology is used in addition with microcarrier. So this requires a growth surface such as a microcarrier for you to have a successful run if you're going to use this spin filter, because most adherent cells needed some kind of surface to grow on. So the spin filter come in various pore size. So this particular one has a 75 micron pore size, and it allows the microcarrier to remain external of the spin filter, while we have a dip tube inside the spin filter, which we pull out media, and while the cell remain attached on the microcarrier to the exterior of the spin filter. This slide here is another technology which we call the fiber cell disc, and this is a proprietary to Eppendorf. It is a promising alternative attachment method. It's 6 millimeter round attachment method made of polypropylene and polyester, and can be used with attachment or suspension cell. The cells are trapped within the layer of the polymer, provide a very low shear environment for shear sensitive cell line, and have a very high surface to volume ratio. Here as well, when you're looking at what we're doing here is we call it noded difference. So we take the most commonly used some of the cell adherence technology in the market and compare it with some of the other spin filter, as well as the 5P, which is the fiber cell technology, to looking at see which one provides you with more growth surface area. So if you look at the most commonly used, like the water bottle, which provides you with 850 total growth surface area cubic centimeter, and you have the 10-layer hyper flask, which provides you about approximately around 6,300 gross surface total gross surface area. And if you were to comparing it with a bioreactor using a spin filter with 30 grams of microcarrier, you can see you have a lot more gross surface area of about 81,000 total gross surface area. And when comparing the fiber cell for the 5P packed bed single-use vessel, you have about 180,000 total gross surface area. So as you can see, by running one bioreactor, whether it's the spin filter or the fiber cell, you have a lot more gross surface area to work with, which in turn will reduce the amount of experiment that you need to do and provide you with more material so you can continue to do experiment. And also really turnaround time is a lot more, it's easier, and it's a better environment because you are controlling all of the parameter, and you're able to maintain all of your process set point within the desired control setting, where with the other technology you may be limited to that. So here we dissecting the packed bed technology a little bit more to show you how the technology is created. So as you can see to the left, we have your traditional stir tank technology, and we have the fiber cell here, which we call the cell immobilization technology. And if you're using a glass vessel, you have the apparatus here to the right and the stainless steel, and you have the fiber cell then compressed in the middle of this apparatus, where the cell then can go and attach to them. And if you go the single-use technology, which we call the 5P to the right, so it's already come pre-gamma radiated, pre-sterile, pre-packed for you. All you do really is open up the bag, remove the vessel out, and connected it to the controller, and you can plug and play, add your media, warm up, and calibrate your sensor, and you can inoculate, and you're good to go. In the next slide here, we're looking at some of the advantage of using a packed bed bioreactor. So you can see a packed bed basket technology is easy and enables working in perfusion mode. So for starter, it's helped with reduced shear forces, and because of its flexibility and concrete gamma radiated, of course, they help reduce time, so you don't have to worry about cleaning, setup, autoclaving. And you also it also provides you with the ability to reduce the loss of cell due to medium exchange, because all the cells are attached to the fiber cell itself. So in return, that provides you with a higher cell density for your seed train, and you have a more healthy cells. Provide you also with higher yield, and you have high mass transfer for nutrient because you're doing perfusion. So which provides you with the ideal environment as well as product quality as well as cells number that you would need to carry on to the next step of your run. In this slide here, the next step is the hands-on expertise for the cultivation of Anchorage-dependent cell. So here we're going to touch base on Vero cells. So Vero cells are Anchorage-dependent. They derive from the kidney of an African green monkey. They typically grown in a tea flask or water bottle. For scale-up, it's usually used microcarrier are used in the bioreactor with pitch blade impeller. The first published record of growing Vero cells in the packed bed bioreactor system was in 2007, which was published in J. Duffy et al. And the Bioprocess International in 2017. Vero cells and vaccine production. Vero cells have been used extensively in the vaccine production since the 1960s. They are susceptible to a wide variety of viruses, include poliovirus, simian virus, rubella virus, reovirus, adenovirus, the influenza virus, and rabies virus. So they are very widely used in vaccine research. Vero cell inoculum facts. Change the medium often. When you change the medium often, that will ensure sufficient nutrient supply and reduce toxic byproduct. Monitoring pH and keep tight parameter. Make sure that you keep a close eyes on your process parameter and maintain a very tight parameter, so that way you can reduce the amount of fluctuations in the parameters that you are controlling. Just like us, they do not like constant changing in the environment. The less time out of the incubator, the better. When you're getting ready for inoculation, try to reduce the amount of time the cells spend out of the bioreactor. This will help prevent the fluctuation of ambient temperature. So that will reduce the shock. That would in turn reduce the lag phase of the culture when inoculate. Keep an eye on the confluency. Vero cells haven't lost their contact inhibition. They stop growing and die if the confluency is reached. So make sure that you keep an eye on the confluency. Next slide, we are talking about the Vero cell cultivation static bioreactor, where we take a look at the cell's expansion in flask for inoculum preparation. The first what we do is we take a cryopreserve, which contains about 5 times 10 cells per mil, and thaw it into one T75 flask, which then later get expanded to 5 T175 flasks, which go into 5 hyper flasks later, and we then inoculate a bioreactor with a spin filter at 5 times 10 to the 6 cells per mil. The condition of the first run we did with the spin filter, we use a inoculation density of 4.8 times 10 to the 5th cells per mil. The working volume was 3 liter. The sparger was a micro sparger. We used the BioFlow 320 control station, as you can see here on the picture in the middle of the screen, which have a gassing strategy of 3-gas auto-gas mixing combined with a flow rate of 0.002 to 0.05 standard liter per minute, and an airflow of 0.002 to 0.2 SLPM, and oxygen flow of 0 to 0.5 SLPM. We also use an overlay with a 3-gas auto-gas mixing of 0.05 to 1 SLPM. Dissolved oxygen set point was at 50%. For agitation, we used a spin filter with a pitch blade impeller at 40 RPM. pH was controlled at a set point of 7.1, plus or minus with Devon of 0.1, and cascade to CO2 as acid source and 0.45 molar of sodium bicarbonate as base, a temperature of 37 degrees. They were grown on microcarrier, and here as well you can see to the right, if you want to pull the application note, you can scan this QR code, which will provide you with the application code and the application note in detail of how we carried out the experiment. Here in this slide, we are showing some successful Vero cell cultivation on microcarrier, starting with the 3rd hour all the way up to day 10. As you can see, from the 3rd hour, the cells started to attach to the microcarrier, and as the culture prolonged, you can see we have confluency in all the cells now attaching to the microcarrier. In the graph below, you can see the total cell density we achieved. We peaked out around 8 million cells per mil. And here to the left, we are showing the metabolic profile, where we were able to keep the lactate under 2 grams per liter, ammonium under 3 millimolar, and glucose, we were able to keep it above around between 3 to 5 grams per liter. Overall, we yielded some of 8 times 10 to the 6 cells per mil, and we had sufficient for the inoculation of the 40-liter Silogen 510 packed bed bioreactor. In this slide, this slide is showing you the Vero cell expansion in the flask for inoculum preparation, where we for the single-use bioreactor, where we took a cryopreserved cells that contain 5 times 10 cells per mil, and tore it into a T175 flask and expand that to 3 T175 flasks, and further expand that into 8 T175 flasks and to 8 hyper flasks, and to the single-use bioreactor, the packed bed system, where we inoculated with 4.6 times 10 cells per mil. Next slide here is showing the setup condition for the single-use bioreactor. The inoculation density for the single-use packed bed bioreactor was at 4.6 times 10 to the 5th cells per mil. Working volume 3.5 liter. We use a micro sparger, and we use similar gassing strategy on the BioFlow 320 as the 3-gas auto-gas mixing. We also use the overlay 3-gas mixing as well. The dissolved oxygen was controlled at 50%. We used the basket impeller for agitation at 100 RPM. pH set point was at 7.1 of plus or minus 0.1 for the dead band. and we cascade to CO2 for acid source and 0.45 molar of sodium bicarbonate, and we control the temperature with a heating blanket at 37 degrees. Here as well, we have the QR code if you're interested in the application note to see how we did the application note, and which have more information on the experiment we conducted in the application lab. You can scan the QR code, which will provide you the link of the application note. So here are the metabolic profile for the single-use packed bed run we did. So as you can see, we were able to maintain lactate under 3 grams per liter. Glucose, we were able to maintain between 2 to 5 grams per liter. And ammonium, we were able to keep it around 3 millimolar. So to the right is showing you the pH profile. As you can see, we were able to maintain a very tight profile of the pH, a very tight control, to say, pardon me, for the pH. As you can see, it was very tidy, hovering around 7.1. Here in this slide, we are showing the result for the 5P bioreactor run we did with the Vero cell. To the left, you'll see we have the total glucose consumption over the 20 days, which was a little bit above around 260 grams of glucose. And when we break it down to daily consumption, in the middle of the graph, as you can see, we achieve hovering somewhere around 23 grams per liter of glucose per day. And when we calculated the cell density over the 20-day period, we were able to achieve around 43 million cells per mil. So as you can see, we were able to achieve a very high cell density compared to the spent filter run we did previously in the previous slide, which lead to a higher, tighter viral production. So in summary, cell culture bioprocessing and perfusion require equipment, the bioreactor with a cell retention device. So microcarrier, spent filter is one technology, and it is easy for cell recovery. The packed bed bioreactor filled with fiber cell discs is ideally suited for the production of secreted products such as protein or viruses by adherent cell. The other common technology used, which we didn't go over too much, and this is also the ATF, which is another cell retention device, is also well suited for the cultivation of suspension cells as well. So at Eppendorf, we has a clear mission for 75 years to improve people's living condition to the current challenge posed by SARS-CoV-2 are therefore both a mission and a motivation for us. We support scientists, researchers, and lab technicians around the world in the fight against COVID-19. So if you want to see what we are doing to contribute and in the fight against COVID-19, here again you have another QR code that you can scan, and that will provide you with more information on what Eppendorf is doing to help contribute to the fight against COVID-19. Here in this slide, we're showing some of the solutions we provide to the industry to help achieve the goal to have expedite the fight against COVID. We have provide solutions from cell storage, liquid handling, preparations, separations, library preparation, screening, sample handling, cell density measuring, pre-culture technology, cultivation technology, and software, of course, for your data processing. And here we provide also solution for the upstream solution, ranging from the R&D scale for the small scale to the process development for the bench scale, and all the way up to pilot production scale bioreactor system as well. Here, if you wanna, we have also another QR code available if you wanna learn more about this, the Cell Expert CO2 incubator for pre-culture. That will provide you with information. And this is the cell incubator. This is the incubator, pardon me, we use to maintain our cells for our run as well, the Cell Expert. The QR code here will provide you with more information if you'd like to see how we use the Cell Expert to maintain our culture. It is uniform temperature for reproducible pre-culture result is verified at 27 spot inside the incubator. It's also ideal for pre-culture. It's optimized for homogeneous growth condition, and it provides a lot of saving when compared to the traditional incubators. If you want to know more information about the controller that we use in our experiment as well, you can run the QR code here to learn more about the BioFlow 320 control station, providing more information about the controller and different configuration and additional information you will need. It is a validated package for the use in GMP environment. It's seamlessly integrated into existing Delta V environment. It's capable of running both autoclavable and single-use vessel. It's equipped with intelligent sensor, so that way it's automatically recognized the sensor and help maintain the life of the sensor as well. As always, if you want to be up to date and to know what event we have going on, and if you want to subscribe to our newsletter, feel free to use this QR code, and that will prompt you to the site where you can record and register your information, and you will not miss any more event. You'll get a email letting you know whenever we have, whether it's a webinar, it's a product release, it's any other event we have planning. We'll be communicating via a newsletter, and you will automatically receive this. I thank you for your time. I appreciate you taking the time to be here, and yeah, I'll take any questions you may have now. Thank you. All right.
Thank you for such an informative presentation, Michelette. Now, before we get started on the question and answer session, I would like to remind our audience how to submit questions. You can submit questions by typing them in the Q&A box, which can be found on the right-hand side of the presentation window. So we'll just give it a moment for some of the audience questions to come in. Okay, Michelette, so the first question we have for you today is, do the cells enter the matrix fiber cell disc, make harvesting complicated?
Yes. So would the cell grow on the surface of the fiber cell disc, and they cannot be harvested until the run is completely done? And if you're using the glass vessel, then you can then completely remove the content of the bioreactor, which include the fiber cell as well as the cell. Then you can use some disassociate agent to remove the cells of the fiber cell disc. That is correct. It is a bit difficult because you don't have access to the cells during the process.
Our next question is, do the cells show different growth rates in the two described systems?
Yes, the cells exhibit different growth rate because it's two different technology. So, for example, the microcarrier run that we did, we do experience a lower cell growth on this technology. If you recall from the presentation that because we're using a spin filter with a pitch blade, and so the mixing is not as quite as ideal as it is with the fiber cell disc and as well as the shear stress. So that may be some of the root cause for the difference in the growth rate. Whereas contrast to the fiber cell technology, the pack bed, the cells trap in the fiber cells this where they get nutrient and fresh nutrient, and also they have been exposed to shear stress, so they are in a more ideal environment, which allow them to grow at a much higher density than you would achieve at the microcarrier route.
And how do you determine the cell density in your process since the cells are attached to a growth surface?
That's a great question. The way we do that, so we use glucose consumption rate, and we correlate that to non-cell density to give us a calculated cell density.
Thank you, Michelle. And now, can you also discuss a bit about why the glucose concentration is going up and down in both experiments?
Yes, that's another great question. Because we, as you know, in both processes, we use what we call a perfusion process where we take the cells in the vessel and we move harvest as well as feeding in fresh nutrients. So as you pumping in fresh medium, which have glucose concentrations in it, so that causing the glucose concentration to goes up, and the cells are then consume it to driving it down. But we also do some supplemental glucose feed throughout the run based on the consumption rate because we don't want them to run out of glucose in the bioreactor. So that's why you're seeing the increase and decrease of the glucose throughout the run in both processes.
Our next question is, why did you reach higher cell densities in the system using the fiber cells rather than microcarriers?
Not a great question. Yes, so ideally the cells naturally like to grow in an adherent surface. And if you look at the fiber cell technology, it's providing them with a more ideal environment where you have in the microcarrier some of the cells, as your cell density increase, now some of the cells are competing for surface area to grow on. So you have not all the cells are getting the right nutrient, are getting the right gas exchange. So therefore, you are limited in terms of surface area where the cell can grow. Whereas in the fiber cell disc, you have a lot more surface area for the cell to grow, which is a more ideal area that the cells prefer. So that's why you see there is a difference in density.
Thank you, Michelle. Now we have a question that asks if you could tell the audience more about the packed bed bioreactor system.
Sure. The packed bed bioreactor system come in two, both single use as well as glass vessel. For the glass vessel, we provide you with a kit, and then you can, along with instruction on how to pack it in the glass vessel and autoclave it, then you can use it for your operation. Where you have the single-use packed bed technology, it come already packed for you, pre-sterile. All you do really is open the bag and put your media in and continue with your operation.
Great. And can these technologies be used with the BioFlow 120?
Yes, both the single-use pack bed as well as the glass pack beds, as well as the microcarrier can be used with the BioFlow 120 as well.
And is the packed bed hard to install, and is there a kit?
It is not hard to install, and yes, there is a kit, and if you order that from us, we provide you with all the parts and consumables that you will need to operate the pack bed and the glass vessel.
Our next question is asking if you could describe the details about the high cell density that you obtained with the packed bed bioreactor, which was equal to 43 million per mil.
Describe, can you repeat the question, please?
Sure. The question is, please, can you tell the details about the high cell density you obtained with the packed bed bioreactor, which was equal to 43 millions per mil?
Yeah, so this technology we've been using that in our application lab within F&F as well as the industry. I mean, they have achieved a lot greater than 43 million cells per mil. But for us, because we are not a pharmaceutical company, we are equipment company, so we mostly try to achieve certain density, and after achieve that, then we consider that success. But you have customers achieving a lot greater cell density using the packed bed system, because it's provided greater surface area to grow for growth, and as well as you are able to use perfusion to pump in cells. To pump in media as fresh medium, which supply fresh nutrients to the culture, as well as while you're removing waste and byproduct that can be detrimental to the cell growth. So that, because of those flexibility and capability of the fiber cell bioreactor, it is really an ideal environment for optimal cell growth.
Okay, now let me just give another moment for more audience questions to come in. Audience members, again, if you'd like to submit your questions, you can type them in the Q&A box, which can be found on the right-hand side of the presentation window. So let me just see and make sure I don't miss any other important questions. Let's just give it another moment. Okay, well, I think those are all the questions we had for you today, Michelle. I guess we will now wrap up our presentation, and I want to thank the audience for attending and for participating in today's event. I would also like to thank our sponsor, Eppendorf, for making today's education webcast possible. Audience members, you will receive an email alerting you when this webcast will be available for replay, and we invite you to forward that announcement to your colleagues who may have missed today's live event. So thank you all for joining, and we will see you again next time. So everybody take care and goodbye.